All right, this is Dr. Morton, and I'm actually recording for the second time this video because I didn't get the right screen up the last time, which totally drives me crazy, but it happens. All right, so anyway, so what we're going to do is we're going to talk about I'm going to work for you the test from spring of 2020. And I've already worked it out. I'm going to go through it again. The other video I posted, I left the wrong screen up the whole time, so that was a problem. And I just didn't realize I was not showing the right screen. Okay, with that, so if you want to see if you want to listen, I'm going to go through a little bit faster this time. So if you want to hear more description, you can play the two videos together, and you can kind of watch on the one and listen on the other, whatever. But anyway, you probably don't need to do that. That's too much trouble. All right, so here we go. So here's the here's the test we're going to do. But I'm actually going to work it off. I'm going to work it off under the camera over here, where I can do it in real time. And I think this is good. So I'm going to slide this over here just a little bit, and I'm going to raise this up just a little bit so we make it just a hair smaller so it'll all fit on at once and you can still see what we're doing. All right. Okay, so I'm just going to point out a few things. Okay, so first off, this is a 4-variable truth table, and here's our F. Remember, F is given to us by God or by your customer, however you want to think about it. So we're going to plot the ones. And remember, we number the squares. So it's 0, 1, flip the bottom two rows, 2, 3, 4, 5, 6, 7. Flip the right two columns, 8, 9, 10, 11, still flipping the rows, 12, 13, 14, 15. This is at the 15th square right here. It's basically in the middle of the map. And you have to do that so that every square connected horizontally, vertically, or wrap around vertically, or wrap around horizontally, but not wrap around diagonally, is connected. So a 1 here and a 1 there are not connected, but ones in all 4 corners can make a group of 4. And of course we know that group of 4 is always B prime, D prime. Okay, so we have a 1 for 0, then nothing for 1, nothing for 2, nothing for 3, 4 is a 1, 5 is 0, 6 is 0, 7 is a 1, 8 is a 1, 9 is a 1, 10 is a 0, 11 is a 1, 12, 13 are both 1s, and 14 and 15 are both 0s. When we look at it, we get this row of 4 up here, we get this group of 4 here, we get this 1 all by itself, and we get this group of 2 here. Every single one there, so that makes 4 prime implicants. There is no other group of 2 that can be combined with this group of 2 to make a group of 4. There's no other group of 4 that can be combined with this group of 4 to make a group of 4, to make a group of 8 rather. There's no other row that can be combined with this group of 4 to make a group of 8. And there's no other box that can be combined with this one to make a group of 2 even. So these are all prime, and this row is C prime, D prime. This group of 4 up here, this group of 4 is A, C prime. This group of 2 is A, B prime, D. And this group of 1 all by itself is A prime, B, C, D. A prime, B, C, D. All right? Okay, so now we can go down here and put the zeros in, and we have a little map here where we can do that. We just copy the zeros off of here and none of the ones, and we wind up with 0, 0, 0, 0, 0, 0, 0, 0. So we have a row of zeros here. That's C prime plus D. Now remember, the way we do this, we pretend, okay, if these were 1s, what would that be? Well, the A and the B would drop. It'd be the 2 variables left would be C and D, and it would be C, D prime. Well, we then invert that, and we get C prime plus D, okay? Because if you take C, D prime, and you invert that, it equals C prime plus D, all right? And then we do that with the rest of them. We have a group of 2 here, we have a group of 2 here, and then we have 2 ways of covering this last 0 right here. One is with this group of 2, and then the other is with this group of 2. These 2 groups to cover this last 0 are non-essential prime implicants. But this row, this group of 2 and this group of 2 are essential prime implicants because no other prime implicants cover, no other cover this 0. This one and this one are covered only by this row, and this one is covered only by this group of 2. That makes these 3 essential, but it makes these 2 non-essential, and then we have to pick either one of these. So for our SOP solution, we just take these terms up here. C prime D prime plus AC prime plus AB prime D plus A prime B C D. And here it is. For the POS solution, we take C plus D quantity times A prime plus B prime plus C prime times A plus C plus D prime, and then plus either or times either A, B, D prime or A, B, C prime. We get a pick. These give you 2 unique but different equivalent solutions. And then when you look at everything, our POS has 1, 2, 3, 4 terms with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 inputs in the first layer, and then 1, 2, 3, 4. So a total of 15 inputs and 1, 2, 3, 4, 5 gates. Here you have 1, 2, 3, 4 gates, same number of gates, but we only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So you have exactly the same. So even though they have different forms, we wind up with exactly the same number of inputs and gates with either the SOP or POS. So they have the same cost. So take your pick. They're going to cost us the same either way. So then you can just do whatever you want. All right, that pretty much covers the first and the second problems here. If we wanted to write the shorthand notation, for the min-term form would be F. Let me write it with a different thing. Would be F equals the sum of the little m's. It'd be 0, not 1, 2, 3, but 4. Not 5, 6, but 7, 8, 9, not 10, but 11, 12, 13. And the POS solution would be, I'll write it up here. The max term solution would be F equals the product of the big M's 1, 2, 3, not 4, 5, 6, not 7, not 8, not 9, 10, not 11, not 12, not 13, 14, 15. Okay, so those would be the shorthand notations. All right. Now, let's look at this MUX problem. So the first thing we do, here's our expression. It's given to us in shorthand notation. So we're just going to plot it down here in our truth table. So we have not 0, but 1, 2, not 3 or 4, 3, 4, but 5, not 6, but 7, not 8, but 9, and 10, not 11, 12, 13, but 14 and 15. And then we divide it into pairs of rows. I'm not drawing the line through the whole truth table. I'm just drawing a little line here. Okay? And then we look at the first two. The first two have the F desired is 0 and 1. 0 for the first row, 1 for the second. That corresponds exactly to D, so we just put D in. Here we have 1 and then 0. That corresponds to D prime, so we put in D prime. 0, 1, that's D again. 0, 1, that's D again. 0, 1, that's D again. 1, 0, that's D prime again. Now we have 0, 0, that's the constant 0. And 1, 1, that's the constant 1. And here's what we put in right here. We just copy those straight in here. And we make sure that our 3 independent variables, A, B, C, not the D, because we're using the D over here, but A, B, and C are put in here. And they select one of the pairs of rows. And that's how we use either, remember there's 4 choices for each pair of rows. D, D prime, 0, or 1. That's all you have to remember, and here's your output F. An 8-to-1 MUX can do any 4-variable function. A 4-to-1 MUX can do any 3-variable function, where we use C here, and A and B is our select line, since there's only 2 select lines in a 4-to-1 MUX. But there are 3 in a 8-to-1 MUX. Okay, that pretty much does that. All right, let's look at the flip-flop here. All right. Okay, and hopefully you could see all that. I think you could. All right, so here's our flip-flop. Notice we do have a bubble and an edge. This is the edge indicator here, so it's an edge clock, and the bubble means it's falling edge. What kind of flip-flop is it? Well, it's got a J and K input, so that makes it a JK flip-flop with a falling edge clock. Does it have an asynchronous set input? Yes, it does, right here. Does it have a bubble? No, so it's an active high set. And the fact we didn't call it a set not should be one of the clues, but sometimes we don't, sometimes it might be mislabeled. But if there's no bubble, then it's asserted when it's high, and when it's low, it's deasserted. So this is an active high set. So is the asynchronous input active high? Yes. All right. Now, if you have gates that only have two inputs, how can you substitute the two gated OR gates for this one 4 input OR gate? Easy. You just have 2 input gates and an output OR gate, and then these are then equivalent. Okay. Now this does add a layer, so that's one downside. But if you don't have 4 input gates, you might have to do this. Here you don't have. You can just do this directly because it's a standard OR. Same with standard ANDs. But with a NOR or a NAND, you must put inverters in between. So we do the same thing here. A, B, C, D, A, B in here, C, D in here. We have the bubbles on the outputs. We have inverters on these, and then we feed them into one more NOR gate with the output F. So NOR gates and NAND gates have to have the inverters in between, but ANDs and ORs don't. You can just replicate them. All right. Now, so we have this map, and we want the minimum solution. So it has 1, 2, 3, 4, 5, 6, 7, 8 ones. We have a group of 4 here. We have a column of 4 here. And that's all we need to cover all the ones. But there is this red group of 4 that's a consensus term. It's a non-essential prime implicant. These are the 2 prime implicants. This group of 4 is A prime C prime. This group of 4 is AB. And this red group is BC prime. So we don't need the BC prime. So our standard solution would be A prime C prime into one AND gate, A, B into the other AND gate, and both going into an output OR gate to give us F. If we have a hazard, because notice we have an A prime here and an A here. So we might have an inverter in this loop, and we could get in a situation where if A changed, there'd be a delay through the inverter. So if, say, A is 1, before this A prime became a 1, there might be a delay. There might be a short time where F would, say, go down to 0 and then come back up. And we would call this a little thing a hazard. And it might only be like 5 or 10 nanoseconds, but there still could be a problem here. And so in that case, we could fix that by adding this BC prime term, which is this red group of 4. And the reason why that works is because there's no A in this term. This is just BC prime. So B would be 1, C would be 0, so C prime would be 1. So this term would stay 1 during this transition, and it would prevent this glitch. All right, here's our Verilog code. The Verilog code would really be written more like E equals A ampersand B ampersand C, semicolon, and then F equals A vertical bar Y, and then H equals E vertical bar F. Normally we put our delay right in here. We would put pound 10 in there for our delays, pound 10 in there. And it's just written it a little differently. And basically we would have one AND gate with ABC going in, one OR gate with A and Y going in, and they would feed into one output OR gate with E and F going in. Okay? Then we have this problem here where we have an expression and we want to plot each of these 4 terms, A, B prime, C, D prime. So A, the first 2 columns here, B prime, this last column, C, bottom 2, D prime, the bottom one. So that's that one right there. Then DC prime. So D is the middle 2 rows. C prime is the top row. So that's all these ones here. A prime, C prime, D. A prime, C prime, D. So A prime, first 2 rows. C prime, upper corner 4 boxes. D, these two boxes here. And then AB, we have this whole column right here for AB. So we plot all these things, and now we can pull these off. Now it wants the max terms, so we're going to pull off the max terms. We're going to pull off the zeros. So there's a 0 on 1, a 0 on 0, not on 1, 2 and 3. So 0, 2, 3, a 0 on 4, not on 5, a 0 on 6 and 7, a 0 on 8, and a 0 not on 9, not on 10, but on 11, not on 12, 13, 14, or 15. All right? So it's 0, 2, 3, 4, 6, 7, 8, 11. And that is our max term notation. Okay. Now you could also work this out in a max term expression. So you'd have a group of 4 here. You'd have this wraparound group of 4 there. You'd have a wraparound group of 2 here and a wraparound group of 2 here. So you'd have 2 variable terms and 2 3 variable terms. And I won't solve that because we didn't ask for that. Here we want to take this expression and we want to convert it into NOR. So we just do a double inversion, and we apply the first one inside here, and we add an OR sign there, and we put ticks on these, so we get the quantity A prime plus C plus D prime quantity prime, ORed with B prime plus D plus C prime quantity prime. So that's 2 NOR gates as our input layer, and then we have 1 output NOR gate for our output layer. Final problem, this one down here. So the first question is, what kind of flip-flop is this? Well, so it is a D flip-flop because of that input. Does it have a rising or falling clock? There's no bubble, so it's a rising clock. Does it have an asynchronous input? Yes, it has an asynchronous set. Is it active, high, or low? There's no bubble, so it's active high. So now we block in all the places where this asynchronous input is active. There and here. So there it's going to block our rising edge. Now let's look at all the rising edge. So here's the first rising edge. It's not blocked, so we draw that down. This one's blocked. This one's not blocked, not blocked, not blocked, blocked, blocked. All right? At this rising edge, our D is 0. Then it goes up to 1. It's 1 here, that down to 0. 0 here, goes up. It's 1 all the way out to here, and then 0 for the rest. So it's 0 here. It's 1 here for this active edge. We ignore this active edge because it's blocked with our asynchronous input. We have a 0 at this active edge. We have a 1 at this active edge, and that's all. And then our asynchronous input is asserted here, so we draw this line down. And our asynchronous input is asserted here, so we draw that line down. We know from the active edge of the clock, we have to wait 5 nanoseconds, so there could be a change here. From the active edge, from where the asynchronous input's asserted, it's also a 10 nanosecond delay. A 10 nanosecond delay there too, so we put in a 10 nanosecond delay. Here we have an active edge of the clock, 10 nanosecond delay. Another active edge, 10 nanosecond delay. Another active edge, 10 nanosecond delay. An assertion of our asynchronous input, 10 nanosecond delay. And finally, that's it. So here, our D is 0, so it just stays 0. It can't change till here, but it doesn't change because it's 0. Here, it can change because of our asynchronous set, so it does go up to a set. Can't change till it gets here, well here, but at this point, our clock locks in a 1, so it stays set. Here, our clock locks in a 0, so 10 nanoseconds after the clock edge, we drop. We stay down till we get to 10 nanoseconds after this edge, where D is a 1 again, so it goes set. Then we assert the set, so nothing really changes here, and we stay set. Here, these are blocked, so we just stay set, and there's no more information. All right, so that's basically, hopefully covers all the stuff that we meant to cover. Okay, so now you have it. All right, so I'll post this. I guess I'll leave the other one up, and I'll change the little thing that says it's goofed up because I forgot to change the screen. So sorry about that. And I'll put this one up, and hopefully this will be helpful to you. All right, so I might even take the other one down. What the heck? It's probably useless. Yeah, I'll take the other one down. All right, so that's the end of this recording, and this was for Friday, the 21st of October, but it is Class Day 25 as well. All right.